All right, continuing on to page 87. We have even larger stars out there, so if we have a high mass star that exceeds 25 solar masses, something really quite extraordinary takes place. Greater than 25 solar masses. All right, so we still have a stellar remnant, which is a neutron star. But in this case, when a neutron star exceeds 3 solar masses, the gravitational pressure exceeds the neutron degeneracy pressure, and it collapses to what's called a singularity. Greater than 3 solar masses. Gravitational pressure. Collapses, so when the neutron star exceeds 3 solar masses, the gravitational pressure exceeds neutron degeneracy pressure, and it collapses to what is called a singularity. This limit is called the Oppenheimer-Volkoff limit. Now, what do we mean by a singularity? Well, recall your high school geometry. You probably encountered a definition of a line as a set of collinear points, and in the course of that discussion, it was probably brought up that a line has no thickness, only length. And so that gets us to what is a point in a geometric sense. What is a point? Does it have any thickness? And the answer is no. And the mathematics of this indicates that that's what a singularity is. It is an object that is so small that it has no size at all. This drives physicists crazy. The mathematicians say, yeah, that's what the math says, and the physicists say, wait a minute, how the hell does that even work? And the mathematicians say, oh, well, you're the physicist, you figure it out. But yeah, that's what the math shows. It's called a singularity. That's pretty significant. Now, we're going to take a little detour here. You may recall that back when we were talking about orbits, we said, what goes up must come down unless you huck it hard enough. Don't forget that. And that is escape velocity. We've talked about escape velocity of gases when a star reaches the AGB phase, for instance, that the gases are far enough from the center of the mass that they reach escape velocity, or the individual atoms reach escape velocity. And so escape velocity is a topic that we've been dealing with now for a while. But let's look at what the arithmetic of escape velocity is. It's pretty straightforward. This is courtesy of Sir Isaac. Escape velocity is equal to the square root of 2gm over r. So there's g, the gravitational constant. There's mass, the mass of the planet or the sun or the moon, whatever, and R refers to the radius, all right? And this tells us how hard you gotta huck something so it don't come back. And we'll get into that here in just a minute. So we're gonna go to the next page.